Okay, let's talk about isotopes. Let's discuss what isotopes mean, how to write their symbols, and then how we can get some information out of those symbols. First of all, let's start with the definition. An isotope is simply an atom of an element. So you can use any element: hydrogen, gold, silver, chlorine, anything. An atom of an element with a different number of neutrons. Okay, so it's the neutrons and the different numbers of neutrons that make isotopes unique. So hydrogen, any isotope of hydrogen must have one proton, but then it can have varying numbers of neutrons. An isotope of carbon must have 6 protons, but it can have any number of neutrons. There are some limits on how many neutrons you can have. That's part of nuclear physics. We're not going to get too much into that this year. That's more of an AP topic. All right, let's look at the symbology used for isotopes. Below you see the isotope notation for a sodium-23 cation. Let's start in the middle. The most informative piece of information is, of course, the element symbol. Those come off of the periodic table. There's a set number of them. And what that then defines is the atomic number. Those two must go hand in hand. They must match. Sodium always has to have an atomic number of 11. And in isotope notation, the atomic number is always written in the lower left-hand portion as a subscript. Now, that number does not have to be there. Sometimes it's assumed to be there. You may not see it written. For example, you may just see sodium cation and then the 23, and the 11's not even there. That's okay, because if we know it's sodium, then we know it has to have an atomic number of 11. The next important piece of information is the mass number. The mass number, if you remember, is the sum of protons plus neutrons in the nucleus of an atom. This mass number is what makes individual isotopes of an element unique. It's the one that changes. Now, this upper right-hand superscript, that spot is always reserved for ion charge. Ions are just atoms that have gained or lost electrons. Isotopes can be ions, ions can be isotopes, or they can have nothing to do with each other. You don't have to be an ion to be an isotope. I'm just showing you that there now because there's an activity at the end of this little lesson that we'll play with pin numbers. But for now, just remember upper right means reserved for ion charge. Okay, let's talk about abundance. Now, what it means to have isotopes is that in nature, if I go out and collect a sample of an element, like in this picture here you see a sample of coal, which is carbon. In this sample of carbon, I won't have the exact same atom through and through. John Dalton in the early 1800s in his atomic theory postulated that, yeah, all atoms are the same, so in this lump of coal here we'd be seeing the same thing through and through. But we've now discovered that's not true. When I have a lump of coal, most of it is carbon-12. 99% of it has 6 protons and 6 neutrons. But you'll see roughly 1% of the atoms in this lump of coal will be carbon-13. 6 protons, but now there's 7 neutrons. Chemically, it doesn't change anything. It's just physically, these carbon atoms are a little heavier. You will also find in any sample of carbon a trace amount of carbon-14, less than 1%. It's actually closer to about 0.1%. But ever so often you'll run across a carbon-14 atom. 6 protons, now 8 neutrons, and now that's too many neutrons. As a result, carbon-14 is unstable, it's radioactive, and you might have heard of it in discussion of radiocarbon dating in biology. Since each element does have isotopes, in any sample, multiple isotopes in any sample, the numbers on the periodic table for mass need to reflect that. As you see here for hydrogen, the number at the bottom isn't a whole number. That's because this is an average mass, an average of the mass numbers of all the isotopes for hydrogen. So let's define average atomic mass. It is a weighted average, which I will show you through an example if you don't remember it from your math class. A weighted average of the mass of all the isotopes. So we have an example here I'm going to work for you, but before I do, let me give you an analogy for weighted average. You have done this before. Let's say that you're in school and for 9 weeks your test average is 100 and your daily average is 70. Well, if your test average only counts for 75% of your grade and your daily work only counts for 25% of your grade, then your average isn't going to be 85. It's going to be closer to the 100 because your tests count more. We have a similar setup here in this problem, so let's see how the math works out. Element X has an atomic number of 10 and comes in 2 isotopes. X20 has a percent abundance of 75%, and X24 has a percent abundance of 25%. Complete a box for element X like you would see it on the periodic table. Okay, so let's draw a box. We need an element symbol in the middle, so this is element X. The periodic table needs an atomic number. We're told that it's 10, so let's put it in a similar location. If you centered it, that's fine. Now we need the mass. Well, I'm not given the average atomic mass. We have to calculate it from the percent abundances this time. So let's start doing that. First of all, we have a 75% abundant, so we'll turn that into a decimal. 75% is 0.75, and multiply it times that mass. So it is X20, the mass number is 20. And then we're going to add that to the contribution of the other isotope, which is 25% of the mass 24. Alright, so 75% of 20 is 15. 25% of 24 is 6. So that works out to be 21. So the average atomic mass of element X is 21. Now in this example I used easy numbers, so we didn't get a decimal. If you look at the periodic table, you will see almost consistently throughout decimal numbers. Alright, let me now show you how to calculate a pin number. Alright, so what do I mean by pin numbers? This is just teacher talk for finding the protons, electrons, and neutrons in any isotope. In this little example here, we are dealing with lithium 7. Okay, if it's lithium, remember bottom left is the atomic number. Lithium has to have 3 protons. Now, I don't see any information in the upper right. When you don't see any information there, you assume that means 0, neutral, no charge, not an ion. Therefore, the number of electrons has to be the same as the number of protons. And then we get the number of neutrons from a little quick formula that is going to be mass number minus atomic number. 7 minus 3 equals 4. There's 4 neutrons in lithium 7. Alright, let's do some more practice here. In the top row, we have cadmium 111 cation. It's a +2 cation. The atomic number is done for us. The mass number is there. 48 protons, 46 electrons. Okay, so we had a +2. So to get 46 electrons, I had to subtract 2 from 48. In other words, there's a deficit of electrons. Now, the number of neutrons is going to be 111 minus 48. Okay, that comes out to be 63 neutrons. The ionic charge is +2. When working problems like this, it doesn't really matter where you start. There's not one piece of information that's more important than the others, with the possible exception of you having to know what element you're dealing with. Maybe the symbol is the most important if you had to give an award for most important. But anyway, we have oxygen 17 in the next row. So if it's oxygen, I know the atomic number is 8. That means the number of protons is also 8. We check that. Alright, next we need to find, oh, nothing else. That one's completely full. So let's go to the next row. We have argon 43. Okay, it's argon. The atomic number has to be 18. Protons has to be 18. The mass number from the symbol is given on top. The mass number is 43. Now let's talk about, well, before I do that, electrons, let's do the neutrons. If there's 43 mass number, 18 protons, that means there has to be 25 neutrons. That's 43 minus 18 to give you 25. Now, back to electrons. There's nothing there, so that we know the ionic charge is 0. Protons and electrons have to match. So there's 18. Okay, on the next row we're given most of our information. We want ionic charge. It's missing. So I just simply look at the symbol. I see a negative sign. When there's no number next to the negative sign, or the positive sign for that matter, you assume it's 1. So there's a -1 ion charge. And notice how the protons and electrons aren't the same. They reflect an excess of electrons. Alright, the last two rows are just a hair more difficult. We're told that we have atomic number 13, but this time we aren't given a symbol. That's okay. We go to the periodic table, look for element number 13. It's aluminum. On the other end of the row here, we're given an ion charge, so we can go ahead and put that as a symbol. And if I know it's a +3 charge and I have 13 protons, how many electrons do you think there will be? Yep, there's going to be a deficit of 3 electrons, or 10. So all we need now is the mass number. We were given the number of neutrons. We calculated protons. So 13 plus 14 gives us 27. And let's complete the symbol with a 27 there. Okay, last one. I know you're getting bored with this, so let's do it as quickly as possible. Alright, I'm missing a symbol for something with atomic number 44. It's a good thing I just wrote through it, but we'll live through it. Alright, so 44 protons. That means the atomic number is 44. We're told the mass number on top is 102. We can go ahead and identify this element from the periodic table. 44 is our good friend ruthenium. How many electrons do we have? According to the symbol is a +1. That means I have a deficit of electrons. So subtract 1, 43. Number of neutrons. 102 for the mass number, 44 protons. So I don't trust myself. I'm going to subtract from the calculator. 58 neutrons. And of course, we've already calculated the ion charge. Okay. And I'm going to leave you with a bit of an analogy. Always beware of the Taylor analogies. I thought of this because the Los Angeles Dodgers have a AAA baseball team in Albuquerque, New Mexico called the Isotopes. And I got to thinking, think of a baseball team as an element. Each player is an atom. Everybody's a little different, but basically the same. They hit, they throw, they catch, they run, but everyone's a little different. So you can think of the players as the individual players as an isotope. So that's a nice little analogy that might help you get through this if you're in the pressure or under the pressure of a test. If you have any questions, be sure to ask me in class.